Okay, this lecture is over Module 6, which covers the data link layer of the OSI model. So if we start out with the introduction to this chapter, why should I take this module? Basically, there's a couple of things here. We're going to, like I said, talking about the data link layer, which is responsible for taking information and placing it on the physical layer and pulling information off of the physical layer at the receiving end. So in the physical layer, we talked about media, and they have one analogy here using a golf ball, that if you get a good hit on a golf ball, it's designed to travel quickly through the air. If you try to move a golf ball through water, it will move through water, just not as fast because of the media and how it was designed. So that's an analogy they use here. So what will we learn in this module? We'll learn to discuss the purpose of the data link layer and what are some of the functions of the data link layer. We'll talk about WAN and LAN topologies, and we'll talk about the PDU for the data link layer, which is a frame. So here is a list of things that we do in the data link layer. So basically, it allows the upper layers of the OSI model access to the physical layer or the media. So it's going to accept IP packets from layer 3. It's going to encapsulate them into a layer 2 frame. Again, a packet is the PDU for layer 3. A frame is the PDU or protocol data unit for layer 2. It's going to figure out how and when it can place data on the media, and then it's going to send those frames over the network media from the source to the destination, possibly going through some intermediary devices. It also is going to perform error detection to make sure that the frame makes it correctly to the destination. The contents have not been altered. So in general, a layer of the OSI model interacts with the layer above and the layer below. So that matches up with our description. Take IP packets from the network layer, encapsulate them into frames, and then put them on the physical media for transmission across the network. So down here in this diagram, they're basically showing you encapsulation, a little more detail. So PC1 is communicating with this web server. The IP packet has source and destination IP. Again, IP addresses are what have meaning at layer 3. When we're at layer 2, it's going to encapsulate by putting a layer 2 header on here. And they say destination NIC and source NIC. I guess that's kind of correct, but it should really say MAC. We have MAC addresses at layer 2 that tell what our source and destination are. Another thing I'll go ahead and mention if I haven't already, MAC addresses are valid on the local area network. That is where they're used. That's what's used to communicate on the local area network. And IP packets go across the internet, capital I, from source to destination. So they cross off the source LAN and go possibly across many networks to make it to the destination. What they're showing us here excuse me, is that the data link layer is divided into two sublayers. The MAC sublayer, MAC stands for Media Access Control, and then the Logical Link Control, the LLC. So they divided this a little differently. The MAC layer is actually what's responsible for, as the name implies, media access or placing information on the physical frame. Ethernet, IEEE 802.3 is what we're going to spend a lot of time talking to, but there's also wireless and Bluetooth. I'll talk about these standards a little. IEEE is the Institute of Electrical and Electronics Engineer. IEEE 802 is a set of standards for computer communications. 802.3 is Ethernet. 802.11 is wireless. And 802.15 is Bluetooth. So those are just the numbers of the various standards that we use at the DataLink layer. Okay. The MAC sublayer, like I said, is responsible for getting the frame onto the physical layer, the media. That's going to include frame delimiting, which is telling us the start and the stop of the frame. It's going to have addresses at layer 2. We're going to use MAC addresses. And then it's going to have error detection. So it's going to add a trailer with a checksum in it so that we can tell if the packet made it, the frame made it to its destination correctly. So here we have some layer 2 functions. It accepts a frame from a medium. This is when it's receiving it. It de-encapsulates the frame, and then it re-encapsulates it if necessary to send it on further on the network. So here we have an Ethernet connection to a router. The lightning bolt is a serial connection. I think we've seen that before, but just in case we haven't. If I play this animation, what's going to happen is we're going to have a layer 2 frame that goes to the router. The router is going to pull off the frame, and it's going to re-encapsulate the packet. So instead of a LAN header and trailer, this time it's going to have a WAN, a wide area network, so that it can travel over the serial connection from the router on the left to the router on the right. When it makes it to its destination, it'll of course rip off this and look at the IP packet that's encapsulated inside of it. There are standards related to the DataLink layer. Like we saw, the Institute of Electrical and Electronics Engineers, IEEE does a lot of these, but ANSI, ISO, and the European ITU also have standards that are at the different layers, and they're showing you the logos for these various standards organizations. 615 is a check your understanding on the purpose of the DataLink layer. As always, you can do that on your own to check your understanding. And we'll move on to topologies. We talked about this previously. I don't remember what module, but physical and logical topologies. The physical topology, which we'll discuss this diagram first, shows where things actually are. Sometimes they'll be on a blueprint. For example, the server room, you'd have a blueprint and it would show exactly what rack it was in, what area of the floor. But this is just telling you within the server room, we have a web server, it's in rack 2, shelf 1. The email server is in the same rack, shelf 2. We have a switch. That switch is connected to a router. We have another switch in the server room that actually serves the IT offices. From this router, we also serve a set of switches that then service 3 classrooms. And the assumption is these classrooms have more than one device in them, but they're just kind of showing you where things are and how they are connected. Now, the logical topology, we're going to have networking information on it. So these various devices that we had before, they're still being shown, but this is network 10.0. Now, if we go back and look, all of this is in the server room, room 2158. But what we care about when we're looking at it from a logical or network standpoint is we have a 192.168.10.0/24 network. So we have a bubble or a cloud here. And within that, we have the web server. A lot of times we would actually have IP addresses of these servers shown. We show on the switch, F is for fast Ethernet. So fast Ethernet 0/1 is connected to the web server, 0/2 to the email server, 0/3 to our file server. And then we have a gig connection, the 0/1, that goes over to our router, and it's connected to gig 0/2/0 on the router. So in addition to network addresses, layer 3 information, we also have information on the various interfaces where these are connected in our topology. As far as WAN topologies, another way topology basically comes from topology maps, which are the lay of the land. There are different topologies that we can have that describe how the network's connected. The first one that's highlighted is point-to-point. It is this port on this router communicates with this. This may be a direct connect, or as we see in a moment, it may travel through some intermediary ports, but we think of it as a point-to-point connection because packets that leave this port on this router are going to make it to this port on this router. We also have a hub and spoke, sometimes called a star, where we have a device in the middle, and then we connect other devices to that topology. And then here we have a mesh topology. This is a full mesh. Every device in this topology has a connection to every other device in the topology, so this is highly redundant. If this connection between this router, which would probably be the preferred connection, is broken, you have 1, 2, 3 more ways that you could actually make it from this router to this router. So this is highly redundant. So that's an advantage. Disadvantage is a full mesh is expensive to create. So as I mentioned before, here we have a point-to-point topology, and there's a network between it, but still anything that leaves node 1 is going to make it to node 2. So this would be the source, this would be the destination. As we see further here, the frames that are going from the source node to the destination node may travel through a cloud of devices. Doesn't really matter what route it takes or what devices are there. The thing we just need to know is if we send a frame from the source node to the destination node, that those frames are going to make it to the destination. So those are wide area network topologies. We'll talk a little bit about LAN topologies. A bus is a very common topology. I don't know if they have a picture of just a bus. They have a modified one. But a bus can be thought of as a straight line, and devices are just connected to it, and those devices share that media. We can also have a ring, which is thought of as a circle. This is their representation of a ring. Typically when I draw a ring, I connect it around PC to PC to PC. So that it doesn't look like a star, but which is shown here. So here we have a star topology. Here we have an extended star where we basically have a bus or a connection, a point-to-point connection between two stars. Here is a bus topology. They have these big connectors here. A lot of times you just draw a straight line here, connect the PC down, and don't have these taps or whatever they're trying to represent. And then a ring topology, the packets go from PC to PC around in a circle. We'll talk a little bit more about that later, I think. The other thing we need to understand is half duplex and full duplex. Basically, in half duplex, with a connection between, let's say, this server and hub that's shown, we can only be transmitting in one direction at a time. In the case of full duplex, we can be sending both directions bidirectional at the same time. So going to play this animation of half duplex. The hub sends to the server turns around and sends to the hub. So basically our bandwidth is cut in half. The main place we have half duplex connectivity is when we have a hub involved in the communications. If we replace that hub with a switch, we're going to have full duplex communications, which, as I said, means we can be sending both directions at the same time. So we can be transmitting and receiving simultaneously, making full use of the bandwidth on the media. The next section talks about access control mechanisms. The access means access to the media. And when we have networks, we can have what's referred to as contention-based access. That means things share media and they may have to try to transmit at the same time. One analogy I explain to my students is getting to the point where a lot of people have never experienced this, but decades ago, especially if you lived in rural areas, in a telephone system, you had what was referred to as a party line. So there might be 5 families that had adjoining property, and they all shared the same telephone connection. The ring might be different depending upon what house the call was going to, but you would pick it up and there might be somebody having a conversation on the phone. So the quote protocol, or the polite thing to do, was just hang up, let them have their conversation, and a little later pick up the phone and see if they or anyone else is talking. If you don't hear anyone talking, then you can make your phone call and carry on your conversation. So that was contention-based for access to a telephone connection. In the case of networking in Ethernet, we have 2 acronyms, CSMA/CD and /CA. So if you take these 2 letters at a time, this is how I remember what the order is and also how I remember what they are. So if we start with the CS, that stands for carrier sense. So that means when a NIC card is going to try to talk on the network, it's going to, quote, listen or look at the network and see if it sees signals like we saw a module or 2 ago, all these different voltages. If it's seeing lots of voltages and voltages changing, it knows somebody's having a conversation. So it will back off, which means it'll wait a few milliseconds and try again. It will listen to the wire. If there is no communications going on the wire, then it's going to assume it's safe for it to transmit its frame. The MA is for multiple access. That means we have multiple machines on the network that are trying to do the same thing. So /CD is for wired Ethernet LANs. That is collision detection. So basically, if I and somebody else, pretending I'm a network device, look at the wire and we don't see anybody talking, simultaneously or almost simultaneously, we can both assume it's safe to talk, and we will both transmit a frame at the same time or close to the same time. And we will have what's referred to as a collision. The collision causes both of the frames to be corrupted or destroyed. The CD, which is collision detection, is a method to detect and handle that. They don't talk about it, but basically they put a jam signal out on the line, which means basically nobody can talk. There's a collision going on. they both back off a random timer amount and then try to retransmit again. They could be involved in a collision again, involved in a collision with a different device. If that was the case, they would just repeat that until they successfully are able to place the frame on the wire. Controlled access, there are two things. This can be token ring, and it can also, well, if they're talking about collision avoidance, that's basically controlled access so that you do not have collisions. So in this figure, we'll talk about token ring. Usually what happens if I'm in the classroom is I grab a whiteboard marker and say, okay, this is the token. In reality, the token is a digital thing, logical thing, and whoever has the token can talk. So when I get the token, I say I can talk, and then I would pass it to a student and say, okay, now that student can talk. When they're done, they pass it to the next student. Now that student can talk. So that's controlling access to the media. As long as everything's working correctly, there should only be one device that has the token, and therefore only one device talking to the network. We also have collision avoidance when we talk about wireless. There's a protocol like a four-way handshake where they basically ask permission to talk, and that permission is granted by the access point. Okay, so we've talked about a lot of this. So basically what happens is PC1 is going to send a frame. What's going to happen is the hub's going to receive the frame. As we talked about in my supplemental lecture, it floods the frames out all the other ports. So this frame will go to PC2 and PC3. PC2 has a frame to send, but it's going to have to wait because it's receiving a frame. And then what happens is the frame is sent out. They will decide whether or not the frame is for them by looking at the destination MAC address. So if the destination MAC address matches, for example, it must match PC3, and it's saying, okay, I will accept that frame and pass it up my TCP IP stack. PC2 will look at the destination and say, hey, the destination MAC address is not me, so I'm just going to ignore that. So basically what they're showing you here is a scaled down version or presentation of how wireless works. Hopefully when we get to the wireless chapter, this will be given in more detail. But basically you can see if devices are talking to the wireless access point. If they are, you don't do anything. If you don't see anybody talking, then you ask the access point, hey, do I have permission to talk to you? And then hopefully the access point responds back and says, yes, you can talk to me. And then it's like, okay, here's the frame I want to send. So you can avoid collisions by having that what's referred to as a handshake. 629 is a check your understanding on topologies, so you can do that on your own. And then we'll move on and talk a little more detail about the data link frame, again, the PDU for layer 2. So basically what happens is if we skip down here, we're going to take data. That data is an IP packet from layer 3, and we're going to put a layer 2 header and trailer on it and then transmit that frame. What they're showing you here in the diagram is from the router to the dish, we will have an Ethernet packet. So we'll have an Ethernet frame. From the dish to the satellite, we have a wireless frame. Satellite to dish, we have a wireless frame. And then dish to network, router, we have an Ethernet frame. So the main thing is, while we're talking about the data link layer, everything that we talk about is a frame. And frame down here, they'll show this in several different ways, but we have data, which is an IP packet. We add a header and possibly a trailer when we encapsulate. In the case of an Ethernet frame, we have a frame start. So a frame start actually starts with something called a preamble and a start frame delimiter. That is transmitted as 8 bytes. What happens is, as you start transmitting, all the receiving NICs, or all the NICs that are going to read this message, kind of have to log on or lock on to the signal. And remember, we talked about bit times and transitions during bit times in a previous lecture. It has to lock onto that and make sure it's reading it. So it may not see the first few bits or the first few bytes, but basically that is 7 bytes of it just sending 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, etc. So it locks on when it knows that it's reading 0, 1, 0, 1. So finally what happens is the start frame delimiter is 0, 1, 0, 1, 0, 1, 1, 1. So whenever it sees those two ones together, it knows that that's the start of the frame. So the frame start is how it locks on and knows where the frame starts. The first thing we have is addressing. And I'll go ahead and tell you that'll be a destination MAC address and then a source MAC address for the destination and source device. The next field is actually referred to as type/length. If it's less than 600 hexadecimal, it is a link. If it's greater than 600 hexadecimal, it's telling the type of frame that is encapsulated, what type of packet is encapsulated in this Ethernet frame. And then control is control flags that deal with things like quality of service. Then we actually have the data we're sending, which most of the time in this class is going to be an IP packet. And then we have error detection. It's called the FCS, the frame check sequence. So basically what happens is, for all the data from the addressing to the end of the data, you perform a mathematical calculation and you get a 32-bit number. Usually you're just adding that byte by byte. If you overflow a 32-bit number, you just throw the overflow away. And then whatever you end up with, you place in the error detection. So what happens is the receiving machine locks onto the frame start, knows where the start frame delimiter is, and then starts reading the frame, but at the same time performing the exact same mathematical calculation. Once it hits the end of the data, it has a calculated checksum. It compares that calculated checksum on the received data to the frame check sequence value that's in the error detection field of the trailer, and then if they match, it makes an assumption that the frame made it from the source to the destination intact. So we've kind of talked about this before. As information travels across the network, as it's going through routers, we will strip off layer 2 headers, look at the layer 3 information, and then re-encapsulate. So we kind of have this up, down between layer 2 and layer 3. So in this case, a host is sending to the router. We have a layer 3 packet inside. We have layer 2 headers. So the layer 3 information, of course, is going to have IP addresses, and this is going to have destination MAC and source MAC. What happens is, when it makes it to router 1, it made it to router 1 because it was the destination in layer 2. It's going to strip off that layer 2 information, look at the layer 3 information and say, oh, I need to pass this data on to go down to the web server. So what I'm going to do is I'm going to put appropriate layer 2 information to say that this port on router 1 is the source and this port MAC address on router 2 is the destination. So I put a new layer 2 on there. When it makes it to this router, it strips off the layer 2 stuff, looks at the layer 3 and says, oh, I need to pass the information out of my right side to make it to the web server. So let me re-encapsulate this packet by putting a new layer 2 source or header on it, and it will have the MAC address of the destination and the MAC address of the source, which this time will be the web server and this particular interface on router 2. So I kind of discussed that, but if you go through and look at the pictures, it's just showing you how it's de-encapsulating and re-encapsulating the frame. 634 is talking about different types of frames that we have. These are older protocols that have mostly been replaced by Ethernet, but we used to have this thing called PPP, which a lot of times you did up or dial-up lines. Frame relay may still exist for serial connections. Asynchronous transfer mode, ATM, X.25. Like I said, these were all LAN and WAN protocols that had their own LAN and WAN frames, and these days have primarily been replaced by Ethernet. So what they're showing us here is that packets will travel through this topology: wireless frame, PPP frame, LDLC frame, frame relay frame, Ethernet frame, and Ethernet frame. So again, frame is used over and over again because that is the PDU for layer 2. So 635 is check your understanding on the DataLink frames. You can do that on your own. This is a short module, so we're now moving on to the module practice and quiz. So what did I learn in this module? This is a summary of the things we talked about. You should read that on your own. And then finally we have the module quiz that's over the whole module, which you can do on your own. So that finishes up Module 6. Watch for the Module 7 lecture on Ethernet switching to appear in the near future.